I'll explain more. When it comes to statistics, usually we are concerned about what happens in the population, and population stands for all the individuals or members of a certain group. However, it is impossible to study the population, and that's why we come up with a sample, a subset of the population. So by studying the sample through inferential statistics, we hope that whatever we see in a sample can be inferred for the population. Okay. So parameter is another term that we use, but this term is of course applied to the population, whereas statistics is any value generated from or applied to a sample. So at the moment we are more focused on the statistics of the sample that we are studying. So when it comes to statistics, we can generally divide them into two types. One is descriptive statistics and the other inferential statistics. So descriptive statistics means when we study the sample, we only describe what is happening to the sample. We do not infer it to the population. We do not try to extrapolate whatever we have learned to the population, but we only uh, constrain ourselves to only understanding the sample that we are studying. So this is describing the data that you have collected from the sample itself. Inferential statistics means you're making conclusions and then applying them to the population, usually by testing of null hypothesis. Okay. So when you test a null hypothesis, you're actually asking the question, what is the probability of finding a difference this large in my samples by chance? Okay, so if the probability is less than 0.05, that means what you are seeing is not by chance. What you're seeing is a significant difference. Okay, so from the word itself, descriptive, you're describing. Inferential, you're inferring what you're looking, what you find from the population, from the sample towards the population at large. Gone through the definitions of population, sample, parameter statistics, descriptive, and inferential statistics. So mainly descriptive statistics describes the sample that you have, okay? Whereas inferential statistics means you are trying to infer whatever you found in your sample to the population. That's why sampling is important. You have to obtain a suitable sample that allows you to generalize to a larger population. That means when you sample, you must be very certain that your sample adequately represents the population at large. Okay, so in a lot of biological studies, this is the weak link. Okay, this is the weak link in the chain, because many times we are not able to obtain good samples, suitable samples that will allow generalization to a larger population. Okay, there are a lot of reasons for this. Uh, Logistic restraints, the availability of the samples itself. Okay, but if possible, uh, you should put more time and effort into designing your sampling itself in order to obtain a suitable sample. So for sampling, you can divide them into a random sampling, representative sampling, or convenience sampling. So random sampling is not as simple as it sounds. Okay, random sampling is not just like taking whatever sample randomly, because even in random sampling, you must fulfill the following statement, where every member of the population has an equal chance of being selected. Okay, so if your random sampling is always constrained to one location or to one aspect, then you are not actually doing uh, a proper random sampling, because you are not really sampling every member of the population. You're not giving every member of the population an equal chance of being sampled. Okay, so please take note that even random sampling is not simply done, but you must make sure that even in random sampling, every member of the population has an equal chance of being selected. Okay, so this is a this is a rule that has to be fulfilled for random sampling, but most of the time, uh, this is not being fulfilled. Okay, representative sampling, which means that you select the cases to match the larger population on specific characteristics. On specific characteristics means if you're studying a particular aspect of the population, then you focus on that and you sample uh, and your sample is and your sampling is done so that you have representative uh, samples based on the characteristic that you are studying. Okay, so this one is where you set uh, the cases uh, in order to match the larger population. Lastly, for convenience sampling, this is based on proximity and ease of access, which means easily, like for example, if you want to study something, uh, but you only sample maybe around the Klang Valley because it's near, it's easier to access. So this is convenience sampling. But how sure are you that whatever is happening in the Klang Valley can be inferred to all the Malaysian population? Okay. So in order to do that, you must ensure that your sample, even though from convenience sampling, does not differ from the population of interest. Okay. Or it does not differ in a way that will influence the outcome of the study. So sampling itself is not so straightforward. Okay, a lot of thought must be put into it so that you do not fall into traps where your samples do not adequately reflect the population. Because if your sample cannot represent the population, then what you are doing is just descriptive statistics. There is no way you can infer what you're getting from your sample to the population. So why are we always targeting inferential statistics? Because your work will be more valuable if you are able to infer it to a larger population. Okay. That's why your work will be more valuable if you're able to infer it to a global population. Okay. But if you're studying diseases, okay, to infer it to the global population, you have to make sure that your sampling is done properly and sample size is adequate and all that. Okay. But you can see that logically speaking, if you're able to infer your work to the global population, that means your work is of course very valuable, okay, in the scientific world. Okay, any questions until now?
No, Doctor.
Okay, thanks. Okay, let's look at the types of variables that you may come across. A nominal scale, no weight on numeric values. This is usually just labels, maybe like Perak, Perlis, Kedah, no? States, name of states, just without any weight or numeric value. Ordinal scale, it has weight but no distance. That means like first, second, third, these are ordinal scales. That means there is weight. First is between first, second, and third, but then the distance between one and two, first and second, second and third, may not be equal. So the unequal interval. Okay, so that is the definition. This is the definition of an ordinal scale. It has weight but no distance, which means unequal interval. So interval scale is where it has weight and distance and also equal interval. Same as ratio, have weight and distance and equal interval. Okay. So next we look at research designs, how you set up your experiments, how you set up your research approach. Usually you can divide them into two: experimental design or correlational research design. So for experimental design, you manipulate your experiment in order to isolate independent variables that cause changes in dependent variables. Okay, so for example, you can change the temperature and look at how the bacteria grow at different temperatures. Okay, then you can infer that how the temperature affects the growth rate of the bacteria. Okay, so you're manipulating the temperature as a variable that causes a, a change in the bacterial growth rate. Okay, this is easy to do, but how do you generalize to the real world? That is hard, because once you culture the bacteria in a microcosm, once you culture the bacteria in a bottle using artificial media, it you are already disconnecting it from the real world. It's no longer there's so it's very hard to infer what you're getting to the population at large. Okay, this is what it means by the difficulty in doing inferential statistics. In carrying out an experimental design where you can generalize to the real world. So correlational research design, you do not manipulate, you do not carry out any experiments to manipulate an incubation experiments, for example, but you just collect data, which means, for example, you collect bacterial growth rate data from the environment at at different temperatures over time. Maybe for example, in temperate countries, during summer it's warm, so you'll get bacterial growth rates when it's warm. Winter is cold, you get bacterial growth rates when it's cold. Then from there, you carry out correlation analysis to see whether the bacterial growth rate actually relates to the temperature, the in situ temperature that you're measuring. Okay, so maybe by chance you'll see, oh, the bacterial growth rate actually increases with temperature. Okay, however, this is not an experiment that you have manipulated. These are just measurements taken from the environment. So you can state that the bacterial growth rate correlates with temperature, but it does not really mean causality, which means how sure are you that the temperature increase actually causes the increase in bacterial growth rate? Okay, other elements, other factors could have played a role. Maybe during summer when the temperatures are higher, there are more nutrients. You don't know. Okay, because this is from the environment, you won't know unless you're measuring it. You won't know because these are not controlled by you. You do not control any of the variables that you're measuring. So this is what it means, that you can show that the variables are related, but you cannot definitively show that it is, you could not definitively show causality, which means the increase in temperature, you cannot show that it is causing the increase in bacterial growth rate. So of course, it is easier to conduct correlational research designs, but harder to draw conclusions. Okay. So usually, uh, yeah, so for ecological research, which my lab does regularly, we do correlational research design. We carry out this more often. However, whenever we see something interesting, some kind of phenomenon that is occurring that we think is because of, which means what we'll do this first, correlational research design. We'll look at the environment, look for patterns and all that. And from there, we come up with hypothesis. Say, is it possible is the temperature that causes the bacterial growth rate to increase? And then we carry out small-scale experimental design where we manipulate the temperature and then we check it out. Okay, to substantiate, to further substantiate the observations that we are getting here. Okay, so that's what we usually do in our lab. Okay, however, this one is still, okay, it is hard to generalize to the real world. Okay, but with experimental design, it strengthens your correlational research design. Okay, makes it uh, it strengthens your conclusions. It makes it easier for reviewers to accept what you are, accept your results in your discussion. Okay, so this is what is uh, what we usually do. So once we have, once we have collected a lot of data, okay, so then it comes to how do you describe them? Okay, so usually when we collect, for example, if you're just measuring bacterial abundance, from one site, you measure daily, you measure hourly. Okay, so how do you describe them? So uh, some form of descriptive statistics. So when you have a lot of data, usually we will describe them first by measures of central tendency. So what is the average? What is the mean? What is the median and the mode? Okay. Usually in normal distribution, okay, in normal distribution or Gaussian distribution, the mean should be equal to the median should be equal to the mode. So if you remember the normal distribution, this has to hold true. Okay. However, in real life, a lot of data, especially in microbiology, does not follow normal distribution. So you will have negatively skewed, where the tail the the tail is at the lower end, and positively skewed where the tail is at the higher end. Okay, I'll show you diagrams about on this later. We also have kurtosis, the shape of the distribution, whether it's leptokurtic, which has a sharper uh, rise, and platykurtic, flatter, and also mesokurtic is the normal one. Okay. Once we know the measures of central tendency, let's just say we choose mean. Okay, we find the average, we found the mean of your sample. Then we need to know the range. Okay, measures of variability can be described as range. Okay, from minimum to maximum, you can also use the first quartile to third quartile range. You can also use variance. However, variance is not the same scale as original measure. So what we usually do is we will square root it to give you standard deviation. Okay, so square root of variance to give you standard deviation, because standard deviation is the same unit as the original measure. That's why in most of the journals you'll see they'll usually report mean plus minus standard deviation. Okay, mean plus minus standard deviation. But sometimes you'll see that they'll report mean plus minus 2 times standard deviation, or mean plus minus 3 times standard deviation. This is just to give your data, um, to give the reader a more accurate description of your variability, because mean plus minus 2 times standard deviation actually covers 95% of your range. Okay, 95%. Whereas mean plus minus 3 times standard deviation will cover about 99.7% of the range. Okay, so it'll give the readers a better idea of how variable your data is. Okay, of course, if you have collected your measurements properly, and in an experiment, if you collected your data properly, the variability should be very small. Okay, so normal distribution is a theoretical distribution. Why is this so important to us? Because most of the parametric statistics that we are using is based on normal distribution. Most of the P, the probability that we had, the probability distribution, the students T-test distribution, the F uh, Fisher's distribution, all are based on uh, your sample being in a normal distribution. Okay, so so we've done this because when we, from normal distribution, if you're doing inferential statistics, we want to know what is the probability of finding a difference this large in my samples by chance. So the standard the standard criteria that we use is probability p less than 0.05. So when the p is less than 0.05, that means what you are seeing is no longer by chance. Okay, what you are observing, what you are testing, what you are observing is no longer by chance. So something, it is significant. Something that you found is significant, is significantly different, is significant because it's no longer by um, chance. Okay, so that's how you interpret your data. So most of the probabilities are based on normal distribution. Therefore, if the distribution is not normal, then the probabilities from normal distribution are not valid. That means if your data is not normal, you cannot use normal parametric statistics. No? What are parametric statistics? For example, your ANOVA, analysis of variance, your students Ttest. All these are based on normal distribution. Okay, that's why however, if your if your data is not normal, you can try to normalize them by try to uh, transform them to ensure that to make so that your data fits into normal distribution. Okay, so for example, some form of transformation for population data, CFU count data, we'll usually just log it, logarithmic transformation. Okay, when we do that, most of the data will tend to fit. After logarithmic transformation, most of the data will fit into normal distribution. Okay, We transform the data so that we can use parametric statistics. Okay, why? Although we have non-parametric alternatives for Ttest, for ANOVA, we have alternatives, non-parametric statistics. However, uh, parametric statistics are more robust. Okay, so it is always recommended that you transform your data so that you can test your statistics using parametric methods. Okay, only if it is no long it is even after transformation you couldn't get a normal distribution, then you have no choice but to use non-parametric approach. Okay, so for example, students t-test is a parametric uh, statistics. Okay, the non-parametric version is the U-test. Okay, Mann-Whitney U-test. Okay, basically, I'm sure you remember, students t-test is to compare two independent samples to see whether the two samples differ significantly. Okay, so sometimes when you have your samples are dependent, usually uh, for trial, clinical trial, before and after, you can use paired t-test. Okay, and also usually when n is less than 120. Okay, so students t-test is found to be good when your sample size is small. For analysis of variance, okay, here we are to compare the means of two or more groups. Usually we use ANOVA, one-way ANOVA, to compare uh, more than two groups. Okay, so you must remember the assumption is normally distributed. Okay, and similar variance. You can use Levin's test to test for unequal variance. However, this one is not available in Excel. It's available in past. Okay, so if your ANOVA is gives you a p less than 0.05, that means among the groups that you are testing, there is significant difference. However, it doesn't tell you uh, which group is significantly different. Okay, that's why you have to do conduct a post hoc test. Okay, for example, Tukey's pairwise comparison or Tukey's HSD. HSD stands for honestly significantly different. Okay, so Tukey's test is carried out only if ANOVA is significantly different. Okay, so yeah, so one-way ANOVA, if your one-way ANOVA is significant, you carry out Tukey's test. If you have more than one factor, two-factor ANOVA or two-way ANOVA, okay, sometimes there is interaction or moderator effects between the two factors. So if the interaction effect or moderator effect is significant, then usually you do not make any interpretation about the two factors because the interaction between the two factors is already affecting your results. So this is parametric. For non-parametric, you can use the Kruskal-Wallis test. Then if the Kruskal-Wallis test is insignificant, you can use the Mann-Whitney pairwise post hoc test or Dunn's post hoc test. Okay, so this is for non-parametric data. So for T-test is comparison of two groups. ANOVA more than two groups. Okay. Other than T-test and ANOVA, you can also carry out correlation. So correlation is a measure of association among the variables. So when you carry out correlation, you'll get a R, correlation coefficient. You can also generate an R squared, which is the correlation index or coefficient of determination. Okay, so correlation, usually what we'll use is the Pearson product moment correlation. This is the parametric statistic for correlation. Pearson product moment correlation. For non-parametric approach, you have the Spearman's rank correlation. Okay, so this is the non-parametric approach. So correlation coefficient has direction, whether positive. Positive means it's going up, the slope. Negative means it's going down. Okay. Significant correlation means there is relationship. However, you do not know whether it's causative. Okay, whether one data is affecting the other. Okay. However, although significant correlation does not mean causal relationship, correlation is a necessary ingredient for any causal relationship. What does that mean? That means from correlation, you can see relationships, but you cannot tell whether there's any causal relationship. However, if you already know there is some causative effect, okay, if you already know from some other experiments, some other literature, there is causative effect, then you should have correlation. Okay, because if it is causal, they should be correlated. Okay. Finally, once you have your correlation analysis, you see that they have a significant relationship correlation. You can actually uh, test the nature and strength of the relationship. For regression, the difference between regression and correlation is for correlation, both the variables are independent. For regression, one of the variables is fixed. Okay, so one is independent and the other is dependent. So the most common one that we use is the least squares linear regression model. We do linear regression because it will yield an equation, usually in the form like this: y equals bx plus a, where b is the slope, a is the intercept. Okay, this kind of equation is useful where you can calculate predicted values. Okay, so it's a simple model, but you can use it to assess change. Predict what will happen if. So when x changes, you can predict what will happen to y, okay, using this equation. The non-parametric version uses a logistic regression. Okay. So this for descriptive, when you want to describe your data, we use this, like what I mentioned earlier: mean, median, mode, standard deviation. When you want to graph your data, graphing data means you want to present your work, your data in a more friendly manner. Okay, because basically, if you just keep putting out data, tables and tables and tables of data, the readers will not be interested, and most of the time they won't be able to see whatever pattern that may be in your data. So association statistics is when you want to see the relationship between your among your data. Like what we are looking at are correlation. So we do correlation. Okay, either Pearson for parametric, Spearman for non-parametric. Okay, linear regression, as I mentioned, is to give you an equation that allows you to model to predict uh, when changes occur. So comparative statistics usually paired or unpaired t-test. So U-test is the non-parametric version. Then you also have your ANOVA. For frequency statistics, they usually use the chi-square. So for Excel, you can use this kind of formula to come up with the mean, median, or mode. Okay, this file is good because this figure is important because it shows you how to choose appropriate statistical tests. Okay, so if you come out with the first thing you have to ask is what kind of data. Okay, so if your data is counts, then they are giving you the chi chi-squared test. Okay, however, for us, we are more interested in measurements. Okay, so we can calculate the average. So we carry out descriptive statistics first to so that we can describe the data that you have. Next, we can test for relationships between two sets. We can plot different kind of graphs. Okay, so when you want to test relationships between two sets, okay, if for normal data we use Pearson, non-normal we use Spearman. Then finding how one factor affects another, we will use linear regression. Okay, so if you are testing for difference between, here we test for relationships, here we test for difference. So if you're testing for difference, if it's normal data, we use Ttest. If it's non-normal, we use U-test. So paired T-test, same individuals, unpaired T-test, different individuals. So as I mentioned, sometimes in paired T-test, if you're doing clinical trial, maybe before and after a treatment, you'll be testing on the same individual, then you can use paired T-test. Okay. So for non-normal, as I mentioned, you can use U-test. And if it's more than two sets, you use ANOVA. If you don't have data analysis here, go to File, go to Options, go to Add-ins, and Excel add-in. Then you tick your analysis tool pack. Once you tick this, you have your data analysis option here. Okay. So this is histogram showing positively skewed, where the tail is at the higher end, negatively skewed, where the tail is at the lower end. Okay. And for histograms showing different kinds of distribution, as I mentioned, mesocritic is your normal distribution. leptokurtic is sharper, and platykurtic is flat. Okay, so that's the difference between uh, mesokurtic, platykurtic, and leptokurtic, and also the difference between positively skewed and negatively skewed. This is what I did. Descriptive statistics. I highlighted the input. I put labels in the first row, and the output, I'll put it here. I click on the summary statistics to give me the summary stats. Usually we just use the mean and the standard deviation. But also sometimes it's good to know the count. If you're working with lots of data, maybe 300, 400 something, sometimes you find that the counts don't match. So once you see that the counts don't match, that means somewhere along the line you've maybe missed out the data or something, or you duplicated some data. Okay, so you have to be very careful when you're working with a lot of data. Okay, and we're not even talking about Excel. Usually I use Excel to handle about 200 over data. But when people talk about big data, they are talking about maybe thousands of. So when you're working with thousands and thousands of sets of data, then definitely you need some kind of scripting language, R or Python, to handle them, because Excel you cannot, you'll be wasting a lot of time, too much time with Excel. But the thing I realized about all this analytics is you still have to know the basics of all the tests. Certain, what kind of criteria should your data meet. It has to be normal. What are the tests for, like for Ttest, comparison of two groups of data. So these are basic things that you still have to know in order to make use of the tools that you have. Okay. Okay. Okay, this is done. Can I move on?
Yes, doctor.
Okay, so now let's go to page 2. So this is, you look at the question, it says compare the mass in, so this is actually data clutch of eggs in a bird's nest. Say, so they measure it in August, they measure it in September. So now you want to compare. Is it different? So this is very straightforward. This is you're comparing two groups of data. Very straightforward. You'll be using Ttest, right? So Ttest, if you drag down your options here, you'll see paired. You are not using paired. You're using two sample, whether it's equal or unequal variances. If you're not sure, just click unequal variances. Click OK. So variable 1 will be here. Variable 2 will be here, right? Label, because you highlighted the label together, so you click here. Yes, the label is inside. Hypothesized mean difference, I say 0, because you can only test whether they are similar. You can't test whether they are different. So we said they are similar. Let's test it out. Then output range, I'll put it here. Okay. Then we click OK. So observations 10, 10. Hypothesized mean difference is 0. Degree of freedom is 17. Your T-stat is minus 2.716. This minus sign here or positive sign here is it just means that the first column is smaller than your second column, that's all. Okay. The positive negative sign is not as important as the value of the T-stat itself. So 2.7, when it's 2.7, it gives you a P of 0.014667. So you see that you have one tail and two tail statistics here. Okay. If you're not sure, always use two tail because two tail is more stringent. Okay. What it means is if it's significant at two tail, it will definitely be significant at one tail. So we always stick to two tail. Okay. So the T stat here is higher than the T critical at two tail. That's why our P is less than 0.05. Okay. That means there is significant difference between the mass measured in August versus the mass measured in September. Any questions?
No, doctor.
Okay. Next, here, compare the mass of birds from 4 different nest situations. So 4. So more than 2. So what must you do? You have to do ANOVA, analysis of variance. So let's check it out. Data analysis. Here you have two-factor ANOVA, ANOVA single factor. So we are only looking at different situations here. No other factors, only one factor. So this is a analysis of variance single factor. Click here. Your input range is here. Okay. Your input range is grouped by columns. And then you have the label in the first row and the output here. Output, let's put it here. Okay. So the situation 1, you have your average and variance for all the 4 situations. Then the analysis of variance show that the F value is 9 with a p-value of 0.0001. That means it is significantly different. Among the 4 groups here, there is significant difference. Okay, so I've already mentioned if there is significant difference, you can then go for post hoc test, Ttest test to check what is the difference. Okay, how it differs. Okay, here you can see that maybe situation 1 is high, but which one is actually higher than? Okay, so we're not sure. Excel doesn't give you Ttest test. There's no menu for Ttest test. In the past, I will do it manually. If you know the formula, you can type the equation and do it manually. But if you have time, I suggest you download Pass. Are you seeing this? The Pass.
Yep.
Okay. So Pass is free. It's very powerful. I usually use it when I want to do multivariate analysis. Okay. Yeah. When you are doing research, maybe in the future, you need to do multivariate analysis, and it's good enough. It has a lot of tests that you can do. When you need multivariate analysis. Of course, the danger here is you must know what you're doing. Don't simply do whatever test is available, because sometimes you might be doing the wrong test. So let's see what pass can do with this set of data. I'll Control C to copy the data. Okay, so this is pass. This is a window. Can you see the like Excel? So you have to click column attributes first, and then paste when your data is here, so that your name is situated here. Then you off it. Then you'll find that the cells are all full with data, and your label is here. Okay. So next I Control A to select all. Go to univariate, and you can see ANOVA. Okay, you can do ANOVA. Okay. Kruskal-Wallis is for non-parametric data. So they don't tell you whether your data is parametric or non-parametric. That you have to find out yourself. Okay. What it gives is it gives everything. So you have to know that your data is parametric. Okay, and that's why you are using ANOVA. So you can see here that the P is 0.000139. It's the same as here in your Excel. 0.000139. Okay, so you're more concerned with the F and the P. Then here you can see that, oh yes, it is significantly different. Now you want to know how they're different. So you look here, Tukey's pairwise comparison. You click here and it shows. Okay, this just shows the different equations that they use. So what is here? Here in the diagonal here, it shows the Q value. Okay, Tukey's test gives Q value. ANOVA will give you an F value. A student's t-test will give you a t value. Okay, so for Tukey's test, it gives you a Q value. This is the Q value, and this is the P, the probability of the Q value. When it's significant, when it's less than 0.05, it's highlighted. So what can we say from this table? We can say that situation 1 is significantly different from 3 and 4. And that's it. No other pairwise comparison is significant. Okay, so it's only situation 1 is significantly different from 3 and 4. Okay, so situation 1 is significantly different from 3 and 4. Okay, which makes sense from the average that you see. Okay, so that's why that's how you can use both Excel to manage your data. Whatever simple test you want to do in Excel, you can do it. Whatever that is too difficult, you can use pass. Okay, so